This will be a review of some things previously covered in general subject matter, but it's good to touch up on it as we enter sheet metal. Reference material for this PowerPoint will come from the AC 43.13 Bravo at section 4 information, so you can use that as a resource, which is downloadable in a free PDF. Material for the majority of structural metals used in aircraft. However, the way the aluminum is alloyed makes a big difference. Aluminum in and of its own does not have sufficient strength to be structural material for aviation. So all aluminums are going to be alloyed with other metals, other minerals in order to get that desired effect. This is a common list of what you'll see alloyed in aircraft grade aluminum. Nations for aluminum is based on a numbering system. And as you can see here, 1 through 9, if it begins with a 1 in this four-letter or four-number code, that's pure aluminum. 2, the major alloying ingredient is copper. By the way, that's the one that is used the most of all the aluminum alloys and structures. And as you go down the list, we get to a 7, which is a zinc alloy, typically 7075. It's used in heavily loaded primary structures, one of the hardest aluminum alloys. If there's an 8 designation, it's going to be a more rare element that's being added. 9 is unused. I like to think that's probably what they're building the UFOs out of right now, some sort of national defense metal. The term clad added to aluminum sheet means that both sides of that aluminum have been coated with an industrially pure aluminum coating. It's very thin, and the reason it's added is pure aluminum is more resistant to corrosion than the alloyed aluminum will be. Now there is a difference. If it is, in this case, if it's a 40 thousandths thick piece of bare alloy, then it measures a true 40 thousandths. However, if it's a clad sheet, on each side, a little over 2 thousandths is used of space to apply the pure aluminum, leaving your alloy at basically slightly over 35.5 thousandths. So if it's a clad sheet, you do lose some strength as compared to a bare sheet of alloy. But the cladding is there to help prevent corrosion. It's engineered into the mix. So the big thing there is if you're working to repair an all-metal aircraft, the FAA question is, what type of metal would you use? Well, we always use the same as original or properly altered. So if it's clad that we're repairing, we will repair with a clad piece of material. And often you'll see terms like all clad. That's just simply the trademark of the Aluminum Company of America. Each company that produces may change the name a little bit, but the term clad means that there's pure aluminum pressed under tremendous heat and pressure on each side of that alloy to make it more corrosion resistant. We must be careful not to scratch it. One of the ways you can always determine clad from unclad is when they ship it. If it has cladding on it, they generally ship it with protective plastic coatings on it. We wait to the last possible minute to pull that protective plastic so that we keep our scratches down to the minimum. One thing to remember, the plastic sheeting is there to protect, and we want to leave it on through our drilling operations. It can be left on for fabricating, but it must be removed prior to riveting. More than once, I've had someone turn in a project, the plastic sheet was still in the stack up, and they've had to go back and drill it apart. So make sure to remove it, but we're going to try to keep it on as long as possible. Any scratches can very easily go through slightly over 2 thousandths of pure aluminum. So if you scratch, and you can see it, chances are it's scratched down to the core material. Not only could it develop a crack there, but it allows corrosion to get in and attack our base material. Designator behind the 4-digit identifier will be our temper designation. Here's a list of common and very important temper designators for different metal, and there's some FAA questions dealing with it. Now, the very first one is O. That means the metal is fully soft. It's not been heat treated to harden it. Many times we desire the metal to come in that way so that forming and bending operations could be done with tighter radiuses. More detail can be formed into the metal without it cracking. Fully annealed material is soft. It's much easier to handle. Usually, we would take a fully annealed piece, do complex shaping, and then we're going to do one or two things after that. It could be sent into heat treat to fully harden it after that, or sometimes the cold working hardens it enough that it's good as it is. It becomes then the -F, and its hardness was achieved as it was fabricated. So O is fully soft, F is as fabricated. If you see the letter T in that designation, it means it's gone through solution heat treatment. They have heat treated it to harden the material. The T3 further specifies how the heat treatment was accomplished. T3 is a common heat treatment. As a matter of fact, 2024 T3 aluminum is the most commonly used structural aluminum. And in some cases, especially if you're working with extrusions, pieces that come in with shape, they will be in the T6 condition. So O, fully annealed. The letter T indicates it's had heat treatment. Numbers following the letter T define what type of heat treatment. F is as fabricated. H, the final one, has been strain hardened. These are some common designations. You need to commit some of this to memory. It's going to be useful on FAA tests. Slide is kind of showing you the difference in some of these heat treating processes. Often the heat treatment varies based on the temperature that the material is brought to and how it's cooled. And different temperatures and different cooling rates produce a different hardness in the metal. This is just showing the example of why a T3 may be different than a T6, may be different than a T4. It's all about temps, times, and cooling rates. Remember from your earlier studies in general subject matter, cold working is changing the shape of a material at room temperature. Now, cold working is generally done after the heat treating results. What it produces is a smaller grain structure. And the smaller and the more uniform the grain structure is, the less brittle the material is and the stronger it is. So it creates a harder, stronger tensile strength than material that was just heat treated and not cold worked. I think the following slide is going to illustrate how once it's put through these rolling systems, the grains will be much more uniform, much tighter, making a stronger material. For annealing in any material is the process of softening the material. And once again, that's a desirable characteristic in some pieces because if we need to make complex shape, if the material's hard, often it'll crack before we can accomplish the shape. So you do see where annealed materials would be necessary. Now, once the annealing's done, it's fully soft. We form it. Like I said before, we may throw it back through heat treatment to reestablish a hardness, or sometimes the cold working strengthens it enough in the forming process that it can go as fabricated, which would be a -F designation. Aluminum, in this case, is elevated to approximately 775 degrees, but it's cooled down in stages. Is a list of common aluminum designations that's used in aviation. 1100 is pure aluminum, commercially pure aluminum. It is generally not used unless it is light trim work. No structural application comes to mind when using an 1100 aluminum. However, this next alloy, which is copper, the first letter, remember, designates the primary alloying ingredient in these aluminums. 2000 series, all of them, copper is your primary. 2017 is a common rivet alloy in aluminum. 2024 is a common rivet alloy, and a 2117 is also a common rivet alloy. As a matter of fact, the 2117 aluminum in the rivets is the most commonly used. There are others such as manganese, the list goes on, and the reason we have all of these varying alloys is if we've got an alloy sheet with a copper primary ingredient, it makes sense to create fasteners with the same ingredients. That way we can avoid the potential for galvanic corrosion. So for every sheet that's produced, they're also going to produce fasteners to align with those alloying ingredients so they'll play well together over the long term. Can use the typical aviation alloys. Magnesium base is 5000 series, 5052 is common. If they add some silicon to it, that's your 6061 materials that's used in aviation and throughout many industrial applications of aluminum. Then finally, our hardest, toughest, meanest would be a 7075 material where zinc is your primary alloying ingredient. I've always found it ironic that some of the things that we need to keep us healthy are also included in these alloys of aluminum. Visually identify any sheet because aluminum sheets would all look pretty much the same, especially if they're clad, is there's ID stripes produced for every sheet of material that meets an aviation spec. Those stripes repeat continually. They're about a foot apart, and they run the full length of the sheets. They run the full lengths of the rolls. In this case, you're dealing with a 2024 T3 clad material. They'll also put other data on the sheet just in case they have a problem. There's traceability back on that batch. That's that AMS and batch number information. It gives detailed information on that specific run of aluminum for traceability. But as you can see here in this picture, this is a sheet of 32 thousandths 2024 T3 clad material. It makes it very easy to identify when you go to a rack that's full of very different types of aluminum. In this particular slide, you'll see that there's a lot or batch number. That's what I'd mentioned before. That's your traceability element. Just like major automotive companies and food companies, all types of industries will have recalls if they find a fault in a product. The same applies to the aluminum they send out for aviation. So by having that lot or batch number, it gives us traceability. And if there's ever an AD issued or a service letter or service bulletin, we can easily determine if it affects the aluminum on the aircraft that we're dealing with. Common aviation sheet thicknesses. The aluminum we use in aviation are pretty much always going to be the same thicknesses. In this case, from about the thinnest we'd ever use, which is a 12 thousandths, up to a 40 thousandths. There'll be more slides in this series that show the different thicknesses. These square footage prices, they're probably not valid anymore, but as you can see, that's 1 square foot of 40 thousandths material at that point in time was $7 a square foot. Well, at $7 a square foot, a sheet of that aluminum would cost approximately, well, 7 times 32 square feet. Sounds like about $234 or so. This is not cheap stuff. Just continues the common thicknesses that are available to us. Now, I will make this one comment, and this will keep you in the cool kid crew. Once your aluminum sheet gets above 90 thousandths, we're reaching that 100 thousandths mark, or that tenth of an inch. Anything above 1/10 of an inch is considered plate. It's no longer called sheet material. You can order different sheet sizes. 4 by 8 is pretty common. 4 by 12 is pretty common. You could also order a roll, at which there could be hundreds of feet on it if you've got heavy equipment to handle it. Also, not listed here, but commonly used, is a 4 by 4. Some shops will order it where they're doing small work. Shipping is a lot less, and it's easier to handle and store. Long and short of it is, if you got the money, they'll sell it to you in pretty much any size you would like to have. This slide sums up the differences in heat treat. We're dealing with the same base material, 2024 copper alloyed aluminum. As you can see in the O condition, the PSI, the strength of the material, is 27, T3 72,000, T4 68,000. That's the reason it is always critical to replace metal with the exact same type. Even though this could be the same thickness, the same alloy, the heat treatment makes a major difference in the strength. As you can see, an O condition compared to T3 is less than half the strength. If you use the wrong material in repair, like these two, you have not completed an airworthy repair. You subject the airframe to possible damage and the people possible injury or death. So reading those data stripes, knowing you have the right material, is a very important part in selecting material to make repairs with. That is about magnesium. It's our little friend that we need in our own systems. But the really cool thing about magnesium is it's extremely lightweight. It of itself is not strong enough to be structural. Yet you add magnesium to aluminum, you get this magical result where it develops a lot of strength and hardness. Magnesium alloys are used all over aircraft, including engine parts, turbine engines, piston engines, where you need lightweight but very high rigidity, very high strength to hold shape. So magnesium alloys are a little more difficult to protect from corrosion, but they do have that property that's very, very desirable in aviation. Therefore, you see a lot of it. Magnesium is kind of a magic metal when you blend with aluminum. There's certainly great properties. Here's some of the disadvantages. Magnesium is at the top of the electrochemical series of metals. Therefore, it will corrode. It will be anodic with exposure to any other metal. In a fist fight, magnesium is going to lose to every metal on the list. Magnesium's also so hard and rigid when blended in with aluminum that it's very hard to form it if it's at room temperature. It'll crack rather than form. So often this thin magnesium parts are formed under temperature and pressure. Thin sheets will crack, and if you ignite magnesium, and I've learned this one through pure experience, it is very hot. It burns very hot, and water will not put it out. So magnesium has its wonderful side, but it also has a dark side, and that slide helps explore some of the negatives. Exemplifies some of the alloy designations dealing with aluminum and magnesium. In this case, we've got a designator that looks very different from your common ones. AZ31 Alpha T4. That's an aluminum plus added zinc. These are very exotic alloys. Of course, they must be handled carefully, and they're very expensive as well. but you produce a material that is super lightweight, super rigid, that it can endure for decades if it's protected and taken care of. Where would a magnesium alloy be utilized since it is more difficult to keep up? Often it was used in flight controls. As composites have come on the scene, they've replaced magnesium because they have the strength to weight that magnesium could produce as an alloy, but they don't have the negative characteristics of corrosion properties. But there are many aircraft out there still flying with flight controls, landing gear doors, floor panels, anywhere they needed a lightweight, rigid structure. For examples, and these are a little more enduring, instrument panels, tanks in general still tend to tend to contain some magnesium because you can create such a lightweight reservoir with it. That's very desirable. But as I said before, composite materials are rapidly replacing them because of the constant need to keep finishes up and continuous inspection to prevent corrosion. Corrosion acts very quickly on magnesium alloys, so your inspection requirement, your intervals are increased as compared to most other. So this is one case that life in plastic can be fantastic, I guess, but I still love my metals.